So far, we have learned about 1 pulse and 2 pulse diode rectifiers. A rectifier is basically a power electronic circuit which converts AC to DC, and the AC voltage which we have seen in 1 pulse and 2 pulse diode rectifiers is a single phase AC voltage, which means that there is one sinusoidal source. When you have a 3-phase input voltage available, that means you have 3 sinusoidal sources available. This is usually the case in industrial applications. So we have a 3-phase supply wherein you have R phase, Y phase and B phase, 3-phase voltages. They are phase shifted by 120 degrees. So this is R phase voltage, and Y phase voltage lags the R phase voltage by 120 degrees, and again B phase voltage lags Y phase voltage by 120 degrees. And when we say voltage, it's obviously between 2 points. So R phase voltage means it is the voltage of the point R with respect to something, it's typically the neutral point. So VRN, VYN and VBN. We can also define line to line voltages, that is the voltage between R and Y or Y and B in a 3-phase system. When you have such 3-phase sinusoidal voltage sources are available, we can realize something called a 3-pulse diode rectifier. Now if you see the circuit here, we have 3 diodes whose anodes are connected to different phases. D1 anode, the anode of diode D1 is connected to R phase voltage source, that is VRN, the positive terminal of VRN, and D2's anode, the anode of diode D2 is connected to Y phase voltage source, the positive terminal of Y phase voltage source, and the anode of D3 is again connected to the B phase voltage source in the positive terminal of it. And what is the other connection? The other connection is all the diodes are joined at their cathode side. So the cathodes are tied together. This is a common cathode connection. And where is the load connected? The DC side load. The load is connected across this common cathode point and the neutral point of the AC voltage source. So this is the configuration for a 3-pulse diode rectifier, which is also known as a 3-phase half wave rectifier. So mathematically, the voltages VRN, VYN, VBN can be expressed as VRN is equal to Vm sin omega t, VYN is Vm sin omega t minus 2 pi by 3, VBN is equal to Vm sin omega t plus 2 pi by 3. And what are the source currents? Because we were looking at the source currents in the single phase also. Here we have 3 currents to look at. That is this current flowing through VRN and the current coming out of VYN, and again the current coming out of VBN. So we are interested to look at IR, IY, IB and also the output voltage that we get. So what is the current flowing through this AC source? It is coming out of AC source, which is IR, which is same as the diode current ID1. Similarly, IY is same as ID2, IB is same as ID3. Again, between these points x1 and x2, we can have different types of loads connected. We can have a R load, which is a simple resistor connected between x1 and x2. Or we can have an L filter, which is followed by a resistive load. Or we can have a C filter, again with a resistive load. Or we can also look at the typical case of a DC motor, which is RLE load. Here in our discussion, we limit ourselves to R load because this half-wave rectifier circuit is also less popular like the single phase half-wave rectifier circuit, but it gives us a good starting point to understand the operation when 3 diodes are connected together. The analysis that was done for single phase half-wave rectifier can be extended in a similar manner to this 3-phase half-wave rectifier as well. Let's try to understand the output voltage. So when you have a resistive load, the output voltage is the voltage across R, VO, And what will be the output voltage? It depends upon the diode states, which diode is on and which diode is off. We all know that if three diodes are connected in common cathode connection, only one of them can conduct, and which one will conduct? Whichever has the highest positive potential at its anode. That means we have three anodes here, R, Y and B points, and if R phase voltage is the maximum among the three, that is VRN, VYN, VBN if we compare them, and if VRN turns out to be the maximum at a given instant, at that instant D1 will be conducting. Of course, as long as this current is positive. This current can only be positive. The current coming out of the common cathode terminal can only be positive or zero. So D1 can conduct when VRN is the maximum among the three. Similarly, D2 can conduct when VYN is the maximum among the three, and D3 can conduct when VBN is the maximum among the three. That is what is shown here. We have the three phase voltages plotted: VRN, VYN and VBN. VRN is having this red color waveform. So VRN is Vm sin omega t. So when t equal to 0 or omega t equal to 0, it starts at 0. And VYN lags VRN by 120 degrees. So the waveform of VYN has a positive 0 crossing 120 degrees after R phase. The waveform of VYN is shown in green color here. And what about VBN? VBN, which is shown in blue color, it will have its positive 0 crossing after 120 degrees from VYN. Now we know that a diode which is connected to the maximum of the three phase voltages will conduct. So which is the maximum of three phase voltages? It keeps varying. For example, from 0 to 30 degrees, in this interval, B phase is the maximum. That is VBN is the maximum. From 30 to 150 degrees, from 30 degrees to 150 degrees of the phase angle, we have R phase voltage, that is VRN, which is the maximum among the three. And then from 150 to 270 or 5 pi by 6 to 3 pi by 2, we have Y phase voltage VYN, which is the maximum. And again from 3 pi by 2, that is 270 degrees to 2 pi and extends to the next cycle, B phase voltage will have its maximum value, that is VBN is the maximum among the three. And the same thing continues in a cyclic manner. So what are the diodes conducting in each interval? D3 conducts from 0 to 30 degrees if you start looking from 0, and D1 starts conducting right at 30 degrees, this point, and it will stay conducting till VRN is the maximum among the three, that is till 150 degrees. And then D2 picks up the conduction. D2 will conduct from 150 degrees to 270 degrees, and then D3 starts conducting. It will conduct from 270 to the 30 degrees of the next cycle. This repeats in a cyclic manner. D1, D2, D3, they keep conducting. And obviously when D1 is on, output voltage is equal to VRN. When D1 is on, VO is equal to VRN. When D2 is on, VO is equal to VYN. What is the procedure? We just apply KVL when a particular state of the circuit is known. We know that the state is D1 on and D2, D3 off. So if you apply KVL, VRN will be equal to VO. That is how we find the output voltage. So when D1 is on, the output voltage is VRN, and when D2 is on, the output voltage is VYN, and when D3 is on, the output voltage is VBN. And what are the minimum and maximum values of output voltage? The maximum value of output voltage is Vm, and the minimum value of output voltage is half of that. Why? Because of the fact that this is 30 degrees. So if you compare with a single phase half wave rectifier or full wave rectifier with R load, we were going all the way up to 0. The output voltage was going all the way up to 0, which does not happen in a 3-phase half wave rectifier. And how does the source current look like? The source current is same as diode current, and since the load is resistive, purely resistive, the current is simply proportional to the voltage. So it's a scaled version of this purple waveform shown here. So ID1 is equal to IR, and it will have only a finite value for 120 degrees, and it will be 0 throughout the remaining cycle. It will be again 120 degrees in the next cycle. And how long does each diode conduct? Each diode conducts for 120 degrees in a line cycle. What do you mean by line cycle? Line cycle is typically one cycle of the AC voltage, that is referred to as line cycle. And what is the average output voltage? The average output voltage can be obtained by this integral. The periodicity is 2 pi by 3. Everything is repeating over 120 degrees. So the periodicity is 2 pi by 3. So it's 1 by 2 pi by 3, and we take from pi by 6 to 5 pi by 6. 5 pi by 6 to 5 pi by 6, the output voltage is just Vm sin omega t, and that will turn out to be, the average value will be equal to 3 root 3 Vm by 2 pi. And what is the peak to peak ripple in output voltage? It is 0.5 Vm as we have discussed, and each diode conducts for 120 degrees. But the input current in each source, IR of t, IY of t, IB of t, will have a finite average value. So if you look at IY would have a waveform in this interval, and IB will have a waveform in the subsequent interval, but it will be 0 in all the other intervals. So every source current will have a DC component which may be undesirable. That is why this half wave rectifier, 3-phase half wave rectifier, is not very popularly used.